This video is on Lewis structures. Lewis structures show the arrangement of valence electrons around atoms in a compound. Just like the formation of ions, 8 electrons is good for most elements to fill their octets. In a covalent compound, atoms achieve octets by sharing electrons. If we were to look at hydrogen, hydrogen has 1 valence electron, so 2 hydrogens coming together will move closer until both their electrons are shared between them. Notice that one hydrogen is sharing the 2 electrons, while the other one is as well. And these electrons are satisfying both of them. Hydrogen has something called a duet because it has 2 electrons. All second period nonmetals achieve octets in stable compounds with diatomics. Fluorine, oxygen, and nitrogen here come together and make diatomics, which are their stable form of the element. So fluorine here has 1 unpaired valence electron, so they come together and fluorine shares both, and we show that by having a single bond between our 2 fluorines. Oxygen shares 2 electrons each, so we have a double bond. Nitrogen shares 3 electrons each, and we show that as a triple bond. So on our bonds here, we can pretend that there's kind of 1 electron here and 1 here. To show the bonds and the electrons moving back and forth. To draw Lewis structures, we have a few rules to follow. First, we must sum the valence electrons of all elements in our compound. Then we'll draw our skeleton. Next, for fill octets, we want to start with the central atom. Then we'll check our number of electrons to see if they add up to our sum total we can start with. If there's too many, we'll take a pair, and make them share, which really means they weren't there to begin with. There's really shared electrons instead. And if there's too few, we'll add electron pairs to the central atom. So let's go through some examples. Here I have hydrofluoric acid, where I have hydrogen and fluorine. We find hydrogen on the periodic table. Hydrogen's in group 1. Hydrogen has 1 valence electron. Fluorine here has 7 valence electrons. Remember, if we ignore the transition metals and we count across 1, 2, 3, 4, 5, 6, 7, 8, that also lines up with our number of valence electrons. So hydrogen has 1 valence electron and I have 1 hydrogen. Fluorine has 7 valence electrons and I have 1 fluorine. That gives me a total of 8 electrons that are valence electrons that will do the interacting in my compound. Then I draw my skeleton, my hydrogen attached to my fluorine, and then I fill octets. Here we don't have a central atom. I know hydrogen only wants to have 2, so then I go ahead and fill fluorine. Fluorine has 2 here, 3, 4, 5, 6, 7, 8. So now that one's filled. And then I check my number of electrons, 2, 4, 6, 8. 8 is how many I can have, so my atom and molecule are happy. Then I have nitrogen, or I have ammonia. Ammonia is made up of a nitrogen and a hydrogen. Ammonia is in group 5, so it has 5 electrons. Hydrogen in group 1 with 1 electron. So nitrogen, 5 electrons and there's 1 nitrogen. Hydrogen has 1 electron and there's 3, gives me a total of 8 electrons. I draw my skeleton, putting my most electronegative atom in the middle, which is my nitrogen. So nitrogen goes in the middle, and then I have 3 hydrogens coming off. Then I fill octets starting with my central atom. Nitrogen needs to have 8. It has 2, 4, 6, so it needs 2 more, which is 8. And then hydrogen all wants 2. It has 2, 2, and 2. So I check my number of electrons. I have 2, 4, 6, 8. 8 electrons, so I'm happy. Moving to my next one, I have methane, carbon, and hydrogen. Carbon has 4 valence electrons. Hydrogen still has 1. So carbon has 4 valence electrons and I have 1 carbon. Hydrogen has 1 valence electron and there's 4 of them. Again, I have 8 electrons. My carbon's going to go in the middle. It's the most electronegative. Then I have my hydrogens coming off. Then I check my number of electrons, I fill octets. Carbon wants 8, and it has 8. Hydrogen wants 2, and it has 2, so everybody's happy with that. I check my number of electrons, 2, 4, 6, 8. 8 electrons, so I'm happy. My next one, I have carbon tetrafluoride. 1 carbon, 4 fluorines. Carbon I know has 4 valence electrons. Fluorine has 7 valence electrons. I have 1 carbon, and I have 4 fluorines. So it gives me 28 and 4, which is 32 electrons. I'm going to put my carbon in the middle. Even though it's not my most electronegative, atoms or molecules want to be symmetric if they can be. And carbon being in the middle will cause 4 fluorines to come on the outside. Also, carbon really likes to have 4 bonds, and that's why it would go in the middle as opposed to the more electronegative element. So I draw my skeleton, and I fill octets starting with the central atom. Carbon wants 8, and it has 8 here. And so then I go to my peripheral atoms, my fluorine. Each fluorine has 2 already, so it needs 6 more. And then I count. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I have 32, which is what I want, so my molecule's done and happy. There's another exception to the octet rule besides hydrogen. Boron can have fewer than 8 electrons. In fact, it prefers to have 6. So if I draw the Lewis structure for boron trifluoride, I have a boron and a fluorine. Boron has 3 valence electrons. Fluorine has 7. So boron has 3 and I have 1. Fluorine has 7 and I have 3. So that gives me 21, 24 electrons. Boron's going to go in the middle, and the fluorines are going to come off. Okay. Boron likes to have 6, so it's happy with the 6 that it has. And then fluorines want to have 8, so right now they have 2, so 3, 4, 5, 6, 7, 8, 2, 3, 4, 5, 6, 7, 8, 2, 3, 4, 5, 6, 7, 8. So my skeleton, and now I've filled octets, and I can count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons, which is how many total valence electrons I had to play with, so my molecule's happy. So when boron's by itself, this holds true, but there's current research being done that shows that boron, after being bonded to 3 atoms, like in boron trifluoride, it will actually still react with a compound if that compound has lone pairs to make a 4th bond. So for example, if water to come along to our boron trifluoride, the lone pairs on oxygen would bond with the boron. They'd be shared between the 2, and then this bond would form. And so boron can make 4 bonds, but only if it's being added to another compound with those lone pairs. Then we can have things like expanded octets. So 3rd period elements can have expanded octet, which means that we're adding more electrons to the central atom than 8. So if we go through our same steps as before, so we have a sulfur and a fluorine. Sulfur is in group 16, so it has 6 valence electrons, and I have 1. Fluorine's in group 7, and I have 6. So that gives me a total of 48 electrons. So my 6 is 32. 42, and 6 is 48. Okay, sulfur is going to go in the middle, and then my 6 fluorines are going to come off. Okay. So I can have 6 bonded to my central atom, and then I fill octets. And then I count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. 48 electrons, which is what it wants. So because my sulfur is central, and it is central because my sulfur has an available d orbital. So typically, if we were to draw our electron configuration for sulfur, looking at the end, we have 3s2 and 3p4. However, because the third energy level also includes the d orbital, my electrons could jump up into higher energy levels, leaving the s and having 3 go into the p, and then 3 more go into the d orbital. So, some more Lewis structure rules, just in summary. Carbon, nitrogen, oxygen, and fluorine always obey the octet rule. They want 8. Boron can have 6. Period 3 elements and beyond can exceed the octet. If an electron remains after satisfying the octet, we put on the period 3 or heavier element, which is our central atom. And if short electrons, we use multiple bonds. I'm going to go over one example where we would use multiple bonds by making carbon dioxide. Actually, by making nitrite. So in nitrite, we have this -1 charge. So if we were to count our valence electrons, we have a nitrogen, an oxygen, and a -1 charge, our components. Nitrogen, being in group 15, has 5 valence electrons, and I have 1. Oxygen has 6 valence electrons, and I have 2. And this -1 charge means we're adding an extra electron. So there's 1 extra electron. So I add these up. 12 and 5 is 17, and 1 more is 18. Then I draw my skeleton, put my nitrogen in the middle, with an oxygen and an oxygen. I fill my octets. Nitrogen wants 8, and so does oxygen. So nitrogen currently has 2. So 2, 4, 5, 6, 7, 8. And each oxygen has 2. 3, 4, 5, 6, 7, 8. And 2, 3, 4, 5, 6, 7, 8. And now I count my total number of electrons. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. That's too many electrons. So I take a pair, and these must not each be lone pairs of electrons. Instead, what really must be happening is it must be another bond. So then I go ahead and draw that. Everything on my left stays the same, but on my right, between this nitrogen and oxygen, I now have a double bond. These electrons stay, as do these. I count my electrons again. 2, 4, 6, 8, because each one of these has 2. 10, 12, 14, 16, 18 electrons. 18 electrons is how many valence electrons my molecule can actually have, so this means my molecule is happy. Because I had to use a -1 charge to make this molecule work, I need to put brackets around my molecule and add a -1 charge to the outside so that my reader knows that an electron was added to make this happen. It does not matter if this double bond is on the right or on the left. Either way is fine. In fact, what we'll learn later is that both of which can happen at an equal probability and will show resonance, which means that it can be over here or over here.